Hello everybody. So today I am going to give a presentation on the topics wave optics. So last time we saw what is ray optics, but the ray optics fails to explain all the phenomena which we are observing in the optical scenario. So here wave optics will help us in explaining some scenarios which were unexplainable using the ray optics concept. So Christian Huygens and Thomas Young were the scientists who were mainly working in the optical area, and they were the one who proposed the wave character of the light at first. So here in ray optics, we were considering the light wave as a ray. That means something which is traveling in the straight line. But here we are considering the wave-like motion of the light. So it will help us in explaining the interference and diffraction phenomena which is happening in the optics. But ray optics fails to explain these two phenomena. So here we will consider it as a scalar wave theory. So the wave optics is useful when the light waves are propagating through or propagating around objects whose dimensions are very close to the wavelength. So here the object dimensions are comparable to the wavelength. So the light propagates in the form of waves, and the velocity of the light in the free space is computed as 3 into 10 raised to 8 meter per second. So since we are considering it as a wave, it has some wave characteristics. So the first one is the wavelength. So the wavelength is nothing but the distance between the consecutive crests or troughs, and the velocity of the wave is c is equal to f into lambda, where c is the velocity of light in meter per second, f is the frequency, and lambda is the wavelength in meter. So in this class, we are mainly talking about the optical frequencies or the optical wavelengths. So this figure will show the entire electromagnetic spectrum, and in that we are interested only in the optical frequencies, which is ranging between the ultraviolet, the visible light, and the infrared region. So the frequency range or the wavelength is varying as per given in the slide. So the infrared region will be extending from 0.76 micrometer to 300 micrometer. The visible region is extending from 390 nanometer to 760 nanometer, and the ultraviolet is ranging from 10 nanometer to 390 nanometer. So the entire range of optical frequencies are from 1 terahertz to 1 terahertz, which is in the far infrared region, to 3 into 10 raised to 16 hertz, which is in the extreme ultraviolet. So this will show the expanded region of our optical frequency region. So the infrared is again divided into far, mid, and near infrared, and the ultraviolet is also divided into 4 different categories. So in the optical wave, it is described mathematically by a real function of position and time. So that is called the Helmholtz equation. And here the position and time dependence, that function is called the wave function. And it satisfies a differential equation which is called the wave equation. That is what is given here as del square u is equal to 1 by c square into dou square u by dou t square equal to 0. So the wave equation is given here. So where the del square will show that Laplacian operator, and the del square is nothing but dou square by dou x square plus dou square y by dou y square plus dou square by dou z square in the Cartesian coordinates. So when we substitute this u of rt, that means the wave function as u r into e raised to I 2 pi ft in the wave equation, then it will convert it into a differential equation of the form del square u plus k square u equal to 0. So this equation is called the Helmholtz equation, where k is called the wave number, and this equation will form the basis of the analysis or the study of the wave in the wave optics. So the different solutions are possible for this equation depending upon the different boundary conditions. Out of that, the simplest solution for the Helmholtz equation is in a homogeneous medium are the plane wave and the spherical wave. And here one more parameter which we need to understand is the optical intensity. Wavelength we have already seen, and optical intensity is nothing but the absolute square of the complex amplitude value, and it does not vary with time. That means if u of r is the amplitude, then mod of u r the whole square will be the intensity of the light. So the main two phenomena which we are discussing here is diffraction and interference. So in the case of diffraction, when the light is traveling or passing through a very small aperture, then the light will try to bend and you will try to move towards the shadow region. So that is what is diffraction means. So diffraction is defined as the interference or bending of the waves around the corners of an obstacle or through an aperture into the region of geometrical shadow of the obstacle or the aperture. So the light waves will bend across the edges or the curvature. So that is what is meant by the diffraction. So here it is showing a single slit experiment in which the light waves the plane wavefronts are shown here. So that will be passed through a very small slit actually. So that size will be comparable to the wavelength of the light. And while passing through that, the light will experience a bending nature actually. So that is what is called the diffraction. And it will be causing the signals to interfere at the incident plane, and the incident plane the intensity will be varying as given in the figure actually. So here it is like a sinc function. So at the middle portion it will be having a maximum value, then it will be decreasing and again increasing, decreasing, decreasing. So like that it will go. So the peaks are called the maxima and the troughs are called the minima of the pattern. And the interference means when two or more optical waves are simultaneously present in the same region of space and time, the total wave function is the sum of the individual wave functions. So that is what. So at the plane, when two waves are interfering at the same time, that will cause the interference pattern. So here we are using a two slits, so which will produce two light sources similar to, it will act as two similar light sources and it will be interfering at the it will be interfering constructively at some points and destructively at some points. When it is interfering constructively, then the maxima will occur, and when it is interfering destructively, there the minimum will occur. So here we are taking two monochromatic waves with the complex amplitudes u1 of r and u2 of r. So it can be represented as u of r is equal to u1 of r plus u2 of r, and the intensity is, as we discussed, it will be square of the magnitude. So I1 and I2 are the corresponding intensities, and at the plane it will be interfering each other, and at that time the intensity will be the square of the sum of the two fields actually. So that is why it is written as mod of u1 plus u2 the whole square. So once we expand this thing, we will get it as the I is equal to I1 plus I2 plus 2 into root of I1 I2 cos phi, where cos phi is the phase difference between the two sources. And when the phase difference is becoming 0, then it will be having I as 4I0, that is the maximum value it is getting. And when the phi is equal to pi, then the minimum value of intensity will be reached, that is nothing but I is equal to 0. So the intensity variation for different phase angles is represented here. It is like a cosine wave. Another thing which we need to consider here is the diffraction gratings. So diffraction grating is nothing but it is an optical component which will help us to modulate the phase or amplitude of the incident wave. So it will act as a modulator here. So it is mainly used in the filters and spectrum analysis and spectroscopy. So diffraction, for example, here it is shown, here they have shown a diffraction grating here. So it is a periodically repeating surface, and when the light waves hit on this material or the surface, the different wavelengths will be directed into different directions. So it will segregate the wavelength content or the frequency content in the signal into different, or it will differentiate the frequency content in the signal. So that is why we are using it in the case of spectrum analyzers. So the diffraction grating directs two waves of different wavelengths lambda 1 and lambda 2 into two different directions, theta 1 and theta 2. So it will serve as a spectrum analyzer or spectrometer. Next comes the interferometers. So the interferometry is a technique which uses the interference of superimposed waves to extract information. So here we are extracting the information after the interference of the signals. So here it uses the electromagnetic waves. In the interferometry typically uses electromagnetic waves and is an important investigative technique in the field of astronomy and fiber optics, etc. So they will help us in extracting the information from the interference pattern which we are getting. So there are mainly three kinds of interferometers. One is Mach Zehnder interferometer, then Michelson, and another one is the Sagnac interferometer. So in the Mach Zehnder interferometer, we are having a laser source. It will be producing the laser or the light which is coming, and it will be hitting on a beam splitter. It will split into two different paths. So then this will be reflected by appropriate reflecting mirrors, and it will be combined by another beam splitter, and it will be received by the detector. So this is mainly used in the case of optical switches and the sensors. We are using the Mach Zehnder interferometer. Then comes the Michelson interferometer. So here we are using a light source and a detector and two mirrors which we are using. Out of that, one will be a fixed mirror and another one is a movable mirror. So the light waves are traveling from the source, and the beam splitter will split the two into two different paths. Both will travel in mutually perpendicular directions, and it will hit the mirror, and it will get reflected back, and again it will be directed by the beam splitter to a detector, and at the detector it will be interfering actually. So this Michelson interferometer is mainly used in the detection of gravitational waves. So the current huge project LIGO is having a very huge Michelson interferometer which is deployed, and it is the core of Fourier transform spectroscopy, and it is mainly used to find out the refractive indices of the medium or to know the movement of some objects. And the Sagnac interferometer means here we are using a laser source, and here it will the beam splitter will split the signal into two different paths. It will be passing through the same path but in a different directions, and then they will interfere each other. And this type of interferometers are used in the case of optical gyroscope. So these are the main things which we need to understand about the wave optics. Thank you.